Cossas from NTHU University, and today I'll bring you about a very exciting topic about the photometrically selected proto candidate at redshift 9, yes 9, in Cosmos working with JWST. And this work was submitted to the PASA and under our revision. So first, I want to begin with why finding protoclusters matters. So first, they are the direct ancestor of the galaxy cluster nowadays. So from the early universe, how they evolve and form to the nowadays galaxy cluster is one of the remaining problem in a modern cosmology, and they account for 50% of the cosmic star forming rate density in a very high redshift. So you know about what's happening in the protocluster, and you know what's happening in the half of the universe. And third, they trace the large-scale structure in the era of the reionization, and which is leading to another interesting model of our universe. So that means finding protoclusters means you can enable a lot of research with the cosmology. And that's next, we begin with the other searches with JWST in the JACE Sears Pearls Matrix program. So this survey covers around 200 square arc minutes, and they found for one overdensity consists of six galaxies at spectroscopy redshift for 5.7, and this structure has a diameter of around 1.7 comoving megaparsec and has an overdensity value of 3.9, which means overdensity is a measurement of the density beyond the field average. So this means there's a 4.9 times denser than the field average. And current record holder is also from JACE. It has a spectral confirmation for 6 galaxies for 8.2 and has a physical diameter around 6 comoving megaparsec, and it's heavily dense, so it's 12 times denser than random volume inside the survey. And another search for protocluster within the SMAC straight 0723 covers only 4 square arc minutes, so it's very, very small. But it has 6 photometrically selected galaxies and 2 galaxies that has spectral confirmation at 7.66, and this structure only extends around for 0.7 comoving megaparsec and has an overdensity around 4, which means 5 times denser than the field average. And so previous surveys only consist of 1/15 of the survey area we will use in this study. So this is a very advantage for us, and this is one of the largest contiguous survey area among all the JWST surveys. So you can see here the SMACs only covers very tiny span of our survey area, and this is good for searching protocluster. And we use a photometric sample from the Cosmos web data release 0.5, which only use half of the Cosmos web. However, you may ask, since it is wide, it might be shallower, but it is possible for detecting the bright galaxy shown in the right-hand side figure that Hubble Space Telescope detected at redshift 10.6. So it is possible to find galaxies at larger than 8. And by integrating the luminosity function from other studies, we expected there's 100 to 1,000 galaxies between redshift 8 to 12. So how to find it? We use the Lyman alpha dropouts, or so-called F115 dropout for designing for detecting galaxies around 8 to 12. You can see that the break has happened to be between the 1.15 micron and 1.5 micron bands. So this is an observing feature from the neutral hydrogen of the vast universe. So combining the previous Hubble Space Telescope and the new JWST dataset, this is a perfect place for searching the Lyman alpha dropouts in this field. And so we use colors for the dropouts to select the dropouts. And we first I have to identify the red break and remove the dusty low redshift interlopers, and also have the constrain the SED shape of this galaxy. And we further reject signal to noise ratio larger than 2 in the lower filters like 0.8 micron and 0.115 micron. Sorry, 1.15 micron. And visual inspected to remove the artifacts remaining that or nearby the large bright sources. And finally, we have around 700 candidates in the Cosmos web field. So next is the most important, one of the most important part of our research to get a probability density function via spectral energy distribution. So by when we obtain the probability density function, we can calculate the chi-square of the reduced chi-square of the each fit, and we selected the difference between the lowest height global minimum and the local minimum that happened in the lower redshift, less than redshift 8, to be higher than 9 to remove the rosy interlopers that mimicking that Bellman break galaxy that mimics the break in the color selection. So in final, we have 367 candidates. So further from the probability density function, we can weight each galaxy number density by simply multiply the probability that dwells, the galaxy that dwells in one of the redshift slices. And here are the results. So at between 9.12 to 9.83, we found one of the most dense region consists of 23 galaxy, 23 Lyman alpha dropouts galaxies, and it has a diameter about 30 common megaparsec, which is 6 times larger than previous record holder at 8.22, and it has, because it has a large scale, so the overdensity only has 2.1 denser than the field average, and this protocol candidate is only around 600 million years after the Big Bang. So it is very new and young. And here I show the top 8 members of the overdensity. You can see that their color is very similar to each other. And in summary, we identified 367 Lyman alpha dropouts among 1,000 square arc million, and is corresponding to 100 times 70 Coulomb megaparsec at redshift 9. And this overdensity has a 2.1 denser than the field average. This is the most distant and young protocol candidate discovered to date. And I'm happy to take questions. Thank you.
thank you very much. Any question or comment? We have lots of time, maybe 5 minutes. Yes, please.
Thank you for your talk. I'm just curious though, because my understanding is that for the proto cluster system, you need to require certain criteria to pass that threshold so that the system will collapse. So I'm just curious whether or not it's just required to have overdensity, or the overdensity need to pass certain threshold in order to be defined as proto cluster.
Yeah.
In this case.
Okay, so yes, that's a good question. So actually, when we're using the this method, the searching radius is important. So if you want to use a larger radius, then you will drop the overdensity value itself. So we test a lot of different scale for this structure, and we found at around the right-hand side figure y equal 5 common megaparsec, which is similar to the previous record holder, we can get easier than 3 overdensity larger than 3. So we think, or community thinks, overdensity 3 is enough to be a proto cluster. Yes.
Please.
Hi, Cossas. Nice work. I have a quick question about the definition of the field here. That means you also have a sample redshift non-field galaxies, and I was wondering if you have an image, how dispersed it compared to the image of your cluster. Is it enough to determine it's a field, or I don't know what I'm asking about specifically actually.
Okay, so first field average means we count every blue stars here, the numbers divided by the green box. So area of green box, and the radius here for the average size is like 15. Is around 15. Sorry. 20 over 20 of the field for data release 4.5. Yes, and I think it's robust enough to detect the overdensity.
Yeah, so that's what, is this the whole field of the whole JWST data set you have? That's my question right now, because no, this is just a part of the...
Yes.
Okay, then it's fine.
Thank you.
Any other questions or comments? Okay, we still have time, but no more questions. Maybe we can go to the next speaker. Okay, so let's thank the speaker again. So thank you very much. And then let's move on.